recursive functions and tree data structure. The topics of discussion are the recursive functions and its implementation in C++, the tree data structure. The subtopics in tree data structure are the terminologies in tree data structure, the binary tree representation in C++, the binary tree traversals, and the binary search tree. Let us discuss recursive functions in C++. Recursion is a function implementation that contains a call to itself. Let's see an example. Finding a factorial of a number is implemented as a C++ recursive function. For instance, the factorial of 4 equals 4 multiplied by 3 multiplied by 2 multiplied by 1, which equals 24. The recursive implementation of factorial receives an integer as input. The function has a conditional statement where when the n is greater or equals 1, the function does the recursive call with n minus 1 as the argument. The function has a base case where the recursion stops. In the factorial function, it returns the value of 1. So, to find a factorial of 4, a call to fact of 4 will be 4 greater than 1, hence the statement implementation will be 4 multiplied by fact of 3. Again, in the recursive call fact of 3, it is 3 multiplied by fact of 2 because 3 is greater than 1. For the recursive call fact of 2, it is 2 multiplied by fact of 1 because 2 is greater than 1. For the recursive call fact of 1, the function returns the value of 1. The value of 1 is backtracked to finding the value of fact of 2, which is 2. The value of fact of 2 is backtracked to find the value of fact of 3, which is 6. And the value of fact of 3 is backtracked to find the value of fact of 4, which is 24. The recursion is implemented by the C++ compiler using the stack data structure. Generation of Fibonacci sequence is another example of recursive function. In Fibonacci sequence, each number is the sum of the preceding two numbers with first number and the second number as 1. So, a Fibonacci sequence of 6 number would be 1, 1, 2, 3, 5 and 8. The C++ Fibonacci generation function is given here as fib, which receives the input n as an integer. When n value is greater or equals 3, the recursive function does the recursive call with n minus 1 and n minus 2 values. When the n value is less than 3, the function returns the value 1, which is the base case because the first two numbers of the Fibonacci sequence are 1. The tree data structure. We'll implement some of the tree data structure algorithms using the recursion. Tree is a non-linear data structure in which the data is not stored in a sequence. The illustration of a tree data structure is as given here. The data in a tree are stored in nodes. The nodes are connected by an edge. Every tree data structure has a unique node called as the root, which is the first node of the tree data structure. The root node occupies the level 0 of the tree data structure. The nodes connected to the root node are the level 1 nodes. In this illustration, B and C are level 1 nodes. The level increase as the tree grows. D, E, F and G are level 2 nodes and H is a level 3 node. The subset of nodes in the tree data structure forms the subtree. In this illustration, the subtree is represented by a triangle. A node is a parent to the other nodes to which it is connected at a level higher than it. As B is a parent node of D, E and F. D, E and F are called as the child nodes for the parent node B. The nodes at the same level are called as siblings. B and C are siblings and they have the same parent. D, E and F are also siblings. They have the same parent B. The nodes which do not have child nodes are called as the leaf nodes. What is a binary tree? In a binary tree, each node has at most 2 children. Given here is an illustration of a binary tree. As you would have noticed, every node has a maximum of 2 children. There are 2 special types of binary tree, the full binary tree and the complete binary tree. A full binary tree is a binary tree in which every node other than the leaves has 2 children. The figure A is an illustration of a full binary tree. The complete binary tree. The complete binary tree is a binary tree if all the levels are completely filled except the last level, and the last level has all the nodes as left as possible. Figure B is an illustration of a complete binary tree. Figure C is a binary tree because every node has 2 children or less, but it is neither complete nor full. Let's see whether we can draw a binary tree with 12 nodes, circle the root and put asterisks at each leaf. An example binary tree would be this. This is my example binary tree, but your binary tree could be any tree that has at most 2 children. This is a complete binary tree because every node except the last level is completely filled and at the last level, the nodes are aligned as left as possible. So, this is the root node. These are the leaf nodes because these node does not contain children. There are two representations of a binary tree. A binary tree can be represented as an array. Usually, a complete binary trees are represented using arrays, otherwise the array would be sparse. The binary tree node can be represented as a C++ class or a structure. How could a nonlinear data structure binary tree be represented in an array? Let's see the algorithm. Step 1. The data at the root of the binary tree always appear at index 0 of the array. Step 2. Suppose that the data for the node appears at location I of the array, then its children, if they exist, always have the data at locations left child at 2i plus 1 and right child at location 2i plus 2. That is, suppose that the data for a non-root node appear at location I of the array, then the data for its parent is always at location I minus 1 by 2. This uses the integer division. Consider the complete binary tree given here. The root stores the data A. In the array representation, the value of A goes to the index 0 of the array. The left child of the root node stores the value L and the right child of the root node stores the value G. In the array representation, when the root node is stored at index 0 of the array, its left child will be stored using the formula 2i plus 1. 2 multiplied by 0 plus 1 results in 1, and the left child value L will be stored at index 1 of the array. The right child index would be deduced using the formula 2i plus 2. Hence, 2 multiplied by 0 plus 2 results in the value of 2, and at index 2 of the array, the right child G would be stored. These two formulae, 2i plus 1 and 2i plus 2, would be applied to every other node in the binary tree. For example, to find the index for the value O in the binary tree, which is stored as the left child of the node L, where L index is 1, the formula for it is 2i plus 1 equals 2 multiplied by 1 plus 1, resulting in 3, and that is the index in which O would be stored. Using those two formulae, all other node values are stored in the array. Suppose if the binary tree is not complete, then there would be spaces in the array. Hence, when the binary tree is not a complete binary tree, it would result in a sparse array representation. The binary tree could be implemented in C++ by representing the binary tree node as a C++ class or a structure. The C++ class or the structure which represents the binary tree node consists of variables that holds the data value of the binary tree node and a left pointer to the left child and the right pointer to the right child, which is of the same data type as the binary tree node. Here is an illustration of how a binary tree would be implemented in C++ with its node values stored as a C++ class or structure. As you have seen, the node is represented with the data value and a pointer to the left child and a pointer to the right child. Hence, the node value A would be stored as a C++ class or a C++ structure with the data field value A, a pointer to its left child and a pointer to its right child. This is applied for every node value in the binary tree. Tree traversal. As we have discussed, a tree data structure represents hierarchical relationships. That is, a root which has child branches which could have their own child branches and so on. Traversal is navigating around the tree and processing the data at the tree nodes. There are three types of binary tree traversals. They are the in-order traversal, the pre-order traversal, and the post-order traversal. In the in-order traversal, the left node is processed before the root node and the right node. In the pre-order traversal, the root node is processed, followed by the left node and then the right node. In the post-order traversal, the left node is processed first, followed by the right node and then the root node. The left, the root and the right are determined considering three nodes of a subtree. In the example given, the leftmost subtree does not have the right child. Here, in the in-order traversal, the left node 3 is processed first, followed by the parent node 1, which is considered as the root of the subtree. It does not have a right child, hence we move a hierarchy up to find the next subtree of 3 nodes. We have finished processing the leftmost node, hence we process the root, which is the 0, followed by the right subtree. We do not process 2 because 2 is the root of the right subtree. We move down to the left subtree of 3 nodes in the right subtree of the entire tree. Here we process 6, which is the left node, followed by the root, which is 4, then followed by the right node, which is 7. Then we move a hierarchy up and take a subtree of 3 nodes. We have finished processing the left subtree, so we process the root, which is 2, and then the right node, which is 5. Similar to the in-order traversal, we do the pre-order traversal where the root node is processed first. Hence, the root of the tree is 0, which is processed first, followed by the other nodes, which are 1, 3, 2, 4, 6, 7, and 5 in that order. Similarly, for the post-order traversal, we process the leftmost node, followed by the right node, and then the root. Hence, the root of the tree 0 is processed at the end. Binary tree traversal is implemented in C++ as a recursive algorithm. Given here is the function inOrder, which does inOrder traversal of a given binary tree. It receives the root node as input and does a recursive call to the left subtree, processes the root node, and does the recursive call to the right subtree. Similar to the inOrder traversal function, the preorder traversal function receives the root node as input. It processes the root node. It does a recursive call to the left subtree, followed by the recursive call to the right subtree. Similarly, the post-order traversal function receives the root node as input as well, processes the left subtree recursively, followed by the recursive call to the right subtree, then processes the root. So far, we have discussed in detail about binary tree in which every node has at most 2 children. So what is a binary search tree? In a binary search tree, the root node value is greater than the values stored at the left subtree, and the right subtree values are greater than the value at the root node. Here is an example of a binary search tree. You can notice that the left subtree values are less than the value at the root node, and the right subtree values are greater than the root node. In figure B, a subtree is highlighted. Here also you could notice the left subtree value is lesser than the root node and the right subtree values are greater than the root node. This principle is true for every subtree in a binary search tree. The C++ class btree builds the binary search tree. It contains 2 functions, insert and insertN. It contains a pointer variable root which is of type btree node. Btree node is a structure which contains the data stored at the binary search tree nodes as data field. It contains a pointer to the left child as left field and a pointer to the right child as right field. In the insert function, when the tree is not null, the insertN function is called with the new value to be inserted and the root of the binary search tree. When the binary search tree is not initialized yet, the new value key is inserted as the root of the binary search tree. In the function insert n, the key value received in the function is checked with the value of the current node. If the value is less, then a recursive call is made to the insert function till the new value is inserted. If the key is greater than the current node data value, then a recursive call is made to the right subtree until a suitable position is found to insert the new value. In this presentation, we discussed about tree data structure, especially in detail about binary tree and binary search tree. In those discussions, we used recursive algorithms to implement binary tree and binary search tree. Thank you.